Section 9.8, the osmotic pressure. I suggest you to Google osmotic pressure and watch some videos on YouTube. It's a lot of fun to see some red blood cells explode in pure water because of the huge osmotic pressure. So first, what's osmosis? That solvent diffuses through a membrane to dilute a solution. So for example, in this diagram, water can get into this solution. We have a membrane here, but this membrane allows the solvent to pass through, not the solute. So I would say this is a semi-permeable membrane. Now, what's the definition of this osmotic pressure pi? That's the pressure raised in the solution. Again, if you look at this diagram, there's additional pressure of pi here. Okay, so you look at this liquid level, you can easily calculate this pi. I think this pi is rho GH. Rho is the density of the solution, G is the gravitational acceleration, H is the height here. And then there's a simple equation to compute this Van Hoek equation, just pi v equals nRT. It's similar to PV equals nRT, but over here we're talking about the solution. This pi is the osmotic pressure, and this N is the solute amount, the number of moles of the solute in the solution. So really it's actually pi equals CRT. C is N of the solute over V. Now let's look at this diagram again. You have pure water outside, let's say it's water, and inside it's an aqueous solution with some solute. And over here, if you look at just this liquid level outside, the liquid level exerts a pressure P. Inside, the liquid level exerts P plus pi pressure because of the height of the solution. Again, because of this additional liquid column, in physics you learned this additional pressure is rho GH. Again, the density times the gravitational acceleration times the height of this column. So it seems the chemical potential of this solution inside is higher than the chemical potential outside, but that's not true because inside and outside are at equilibrium right now. So what's going on? Well, inside you have a solution. Remember, the mole fraction of the solvent is less than 1. It's less than the mole fraction of the solvent outside. Lower mole fraction results in lower chemical potential. So if you look at this level, true, it has a higher chemical potential because of the additional pi, but it also has a lower chemical potential because of its lower mole fraction. So these two cancel. Now we're gonna prove this Van Hoek equation right now. So let's look at the inside liquid level. It's equal to, this is the chemical potential of pure water outside, and this is due to the lower mole fraction inside. Okay, so this mole fraction is less than 1. And this gives you the chemical potential increase due to the additional osmotic pressure pi. Alright, so we got chemical potential decrease, chemical potential increase. Okay, outside it's just mu I star. Okay, outside it's just mu I star. So this is inside, this is outside. So when the inside and outside reach equilibrium, the solvent stops to diffuse through the membrane. We have this inside the chemical potential being equal to this outside. And mu I star, they cancel. Therefore, this plus this is 0. We got this equation here. And then x of I is the mole fraction of the solvent. So it's 1 minus x solute. And therefore, we can have this equation. And if you know how to do Taylor expansion of this, ln 1 minus x is simply negative x. If you don't believe me, use your calculator, compute the logarithm of 1 minus 0.01. The result is 0.01. The logarithm of 1 minus 0.00001 is, well, negative 0.00001. So just double check this. This is just the Taylor expansion of the natural logarithm. And then we have this approximation here, so it's pi v equals RT x solute. Over here, this is molar volume, molar volume, molar volume, remember, because mu is molar Gibbs energy. Now we just need to multiply both sides by the total number of moles, and then we get pi v equals RT times n solute, approximately. Alright, so again, this is similar to PV equals RT, so if you can't remember this equation, remember PV equals RT and replace P with pi, and then replace this N with N solute. Alright, this is a colligative property, so it does not depend on the nature of the solute, it just depends on the number of moles of the solute. And actually, we should divide both sides by V. And then you have pi equals CRT. C is just the molar concentration of the solute. Alright, so actually this equation is simpler. The osmotic pressure is equal to the molar concentration of the solution times R times T. Now, if you have, again, 1 mole sucrose dissolved in let's say 10 liters of water, you have 0.1 molar concentration. That's actually very high concentration. You just plug in this 0.1 mole per liter, and this R is 0.08 bar liter per mole K. Let's say the temperature is 300 Kelvin, and then you have 0.1 times 0.08 times 300. I think the result is 0.25 bars in the end. So the osmotic pressure is pretty high. It's 0.25 bars if you add only 1 mole sucrose in 10 liters of water. Well, what if you add 10 moles of sucrose into 10 liters of water? Then the osmotic pressure is going to be 2.5 bars. That's actually even much higher than the ambient pressure. You can increase the pressure from 1 bar, the liquid outside the membrane fills, to 3.5 bars. That's a huge pressure. That's why if you put red blood cells in pure water, they're going to explode.